we're going to continue with a new lesson of HCIP-AI. In the last lesson, if you missed the last lesson, please make sure that you go through the recordings on the YouTube channel. So we're going to go back to what we did last time, pick it up from there. So the last thing that we did was the Kenny age detection algorithm. So mentioned that the Kenny age detection algorithm is composed of 5 steps. So we use the Gaussian filter to smooth the image and reduce the noise, calculate the gradient intensity and the direction of each pixel in the image, use non-maximum suppression to eliminate the spurious response caused by edge detection, and then use double threshold detection to determine real and potential edges, and then suppress isolated weak edges to complete edge detection. So that was just for edge detection. So today we're going to talk about a geometric transformation of images. So basically, we need to understand in a geometric transformation of images, we're going to actually deal with the position of the image, what's the size, the shape, how the shape is going to be changed through mathematical modeling, right? So that is very important for us to understand. So when we're talking about geometric transformation, so what we need to understand by that is that the geometric transformation of images is one of the key concepts in image processing and AI, because this is where an image is reshaped and reoriented. We can reorientate the image without changing its pixel intensity value. So that is one thing that is very important for you to know, that when we're doing a geometric transformation on images, the image is reshaped without changing the pixel intensity value. So this is important for image alignment, image augmentation, and pre-processing in computer vision tasks. Okay, so what is a geometric transformation? So if we have to define it, we can say it's the process of mapping an image from one coordinate system to another coordinate system. So we only change its position, size, orientation, and shape, but we don't change the intensity of pixels. So that is a geometric transformation of image. So in AI, geometric transformation will help models recognize objects despite variation in rotation, scale, or perspective. All right, so we have many types of geometric transformation. You can have like a translation, a scaling, resizing, rotation, shearing, reflection, flipping, affine transformation, perspective transformation, and so we have different type of geometric transformation. All right. So very important to note, when we have like the affine transformation, which we're going to talk about today, and so basically the affine transformation will just be the method we're going to use, the geometric transformation, but in this case we're going to perform a linear coordinate transformation. So we're looking at the coordinates of the sizes of the picture. So we're gonna consider transform the linear coordinate, right, on an image which is in 2 dimensions. All right. So an affine transformation will basically be a transformation that will preserve the point, straight line, and parallelism, but may change the position, the scale, the rotation, or the shear of an image. So affine transformation are widely used for image alignment, pre-processing, and data augmentation. So what is an affine transformation? So basically, this is just a linear mapping between two coordinate systems that will preserve the parallel line, which will remain parallel. Ratio of distance along the line remain constant as well. So unlike the general transformation, in this case, angle and length may not be preserved. All right, so we're going to change the angle and length, but it's preserved. If there's two lines that are parallel, they remain parallel. And so that is an affine transformation of the picture. All right, so in this affine transformation, we can have a translation, which means move the image along the X or Y axis, or rotation, which means we rotate the image around a point, or scaling, which means we enlarge or reduce the image, or shearing, which means we can just slant the image along X or Y axis. So affine transformation cannot represent perspective distortion. So that is very important. So when we think of it and in an analogy with human eyes, the human visual system can recognize objects regardless of the rotation. If you take a dog, you rotate the dog, the human mind can still identify it as a dog, right? So affine transformation in AI will help achieve similar invariance. So even if an image is rotated or there's any issue like that, we can still recognize the image, right? So models can detect the same object under different orientation or sizes. All right, so that's what we have. So an affine transformation is just a combination between a combination of translation, rotation, scaling, and shearing. And then we preserve all the parallelism and ratio along lines, but angles may change. So this is very crucial in AI for invariant object recognition, image alignment, and data augmentation. So when we looking at affine transformation, so we understand we just have to change this coordinate and keep the parallelism and things like that. All right. So, okay. So, and then we have other type of translation. This is an example of the affine translation. So this is a transformation, an example of a QR code. Remember now you can try and scan the QR code. It's not always going to be straight. It can be in a different orientation, but the machine can still recognize it. So that's what it does. So it's going to take this picture and put it in a proper position without changing anything. So the ratio can change. That means that everything can be enlarged. So the width and the length can be enlarged at the same ratio. So yeah, so that is an affine transformation there. Right, so the next one will be scaling. Scaling means that we have an image with a certain resolution. For example, the resolution here is WH, which is scaled to 1 with a resolution H here. So in this case, the horizontal scaling factor is SX, and the vertical scaling factor is SY. So basically what's going to happen here, we're going to have a transformation matrix for scaling A. So the image here, so we had, for example, here 252 by 252, we end up with 512 by 512. So this was scaled twice. So we have the X will be double, the Y will be double. So this is scaling of a picture, so which is a transformation process as well. Okay. Right. And then we can look at amplifying an image proportionally. So when we talk about amplifying an image proportionally, what we mean by that is we are actually looking at how we can transform the image, right, in a certain uniform scaling. So the transformation, the amplifying an image proportionally is also called uniform scaling, right, or proportional resizing in image processing and AI. because it's the geometric transformation where an image is enlarged or reduced while maintaining its aspect ratio. All right, so the width and the height increase or decrease by the same factor. So what is the proportional amplification here? So we're basically resizing an image so that all the dimensions are scaled by the same factor, which means we are preserving the original shape without distortion. All right, so the aspect ratio can be like width divided by height. So that's ratio remain the same. So if, let's say, for example, the width was double of the height, even if uh, we modify, we transform the picture, we scale it. If we use a uniform scaling, it means the width is still double of the height, despite the fact that the width has changed and the height has changed. So that's what this means. All right. So why proportional amplification is important? Because it's going to prevent distortion. Example, when we are stretching or squashing the image, right? It's going to maintain that relative position of object in an image. Because sometimes you look at a big image, a certain object need to be on a certain position from image. So when we're transforming the images, we don't want to change that proportion because now it's not going to make sense on the image. So this is useful for AI models that require uniform input sizes. Okay, so when we think about it in an analogy with the human eye, when human enlarge an image on a screen or zoom with lenses, the image appear larger but undistorted. Okay, so AI proportional scaling mimic this, so which is preserving the structure and all the features. So this is very important because we use it in applications like in AI, like things like CNN. Um, so this will help with resize images to a standard size without distortion. Okay, we have it in image augmentation where we can zoom in or zoom out for training data sets. We use in medical imaging, satellite or aerial imaging, document processing, so where we can just resize scan pages proportionally uh, for document that we may be trying to scan. Okay. All right. So it means that in real life, how it's going to work is that we're going to have to determine a scaling factor, right? And then we multiply all the coordinate by that scaling factor because everything needs to keep the, okay. All right. So, and then from there, we will have what you call this. Okay, so that's amplifying an image proportionally. And then from there, we're going to have interpolation. So when we talk about interpolation, so we need to note that when you're looking at an image, the digital image, the values X and Y, which are the size of the image, in a digital image are integers. So what does it mean, integers? It means we have numbers that are integers, right? Uh, Normal numbers, integers from the integers class, but the coordinate obtained after we've done a coordinate transformation may not be integers. That means we may have a picture which is 20 by 20, but because of the transformation we've done, we end up having a picture which is a 20 point something, 20.5 by 20.6 example. So we now have numbers that are not integers. So for us to make sure that we remain with integers, we need to introduce a fundamental concept in image processing and AI, which is interpolation. That means that interpolation comes to play uh, whenever an image is resized or rotated or we have done a geometric transformation. So this is the process of estimating new pixel value based on existing one. So interpolation will basically be the method of computing the intensity value of pixel at a known integer or a known location using nearby known pixel values. So this is needed whenever the new pixel grid doesn't align exactly with the original grid. For example, during scaling, during rotation, or translation. So why is interpolation important in AI? Because during resizing, rotation, or geometric transformation, some pixels may fall between original pixel coordinates. So as I said, instead of having a 20, we have a 20.5. So we need to interpolate like a 20.8. We need to see, okay, 20.8. What is it close to? Is it close to a 19 or it's close to 21 or close to 20? Then we see where it fell. So interpolation will just allow the AI system to estimate this pixel value, preventing gaps and jagged edges, right? So this will ensure smooth images for feature extraction and model training. All right, so at the type of interpolation that we're going to have, we can have a nearest neighbor interpolation or bilinear interpolation, bicubic interpolation, or other interpolation methods. So basically, in the analogy of the human eye, human vision can estimate colors or intensity in the region between observed points, especially when you are zooming in, right? So interpolation mimics this behavior to produce continuous or smooth images. So we so that's interpolation. So you need to understand when we're talking about interpolation, we are talking about getting the right value in terms of the integer value. So it's kind of estimating whatever we have and placing it close to where it's supposed to be. You have your by linear interpolation here, um, which will follow a specific method. So it's gonna use the four nearest pixels, a 2 by 2 neighborhood to compute a weighted average. So the good thing about this, you have smooth images better than the nearest neighbor method, but the problem is the image can be slightly blurry. Okay, so it's mostly used in image resizing and for AI pre-processing. So that's it with the um, bilinear interpolation. So um, that's how it works, right? All right, and then the next one would be a translation. So in translation, so we basically have a certain point with um, this coordinate x, y in an image. So, and then we translate it there. So the coordinate of the new image will be there. So translation, just that on the normal frame, the picture has moved. So it has been translated to different coordinates, but it keeps the same size. It does not increase without, we do not increase the size or anything like that, but we keep it there. So basically translation is one of the simplest geometric transformation in image processing and AI, which involve just shifting an image or object from one position to another position without altering its shape, the size, or orientation. So translation will actually move every pixel of an image by a fixed distance along an x-axis and y-axis. So it doesn't affect the intensity values of pixels or structure of the image. All right, so mathematical representation of that. So we basically gonna have, maybe we have x. So the new x will be the previous x plus the value, the translation distance. All right. And then the new y would also be y plus the translation distance in the y on the y axis. So that's how the image is is being translated. So an analogy with human eyes, so it's like moving an object across your field of view without changing its sizes or shape, right? So that is translation there. Okay. All right. So and now the next one will be the reflection. So the reflection, so in this case, we also do a transformation of this, but the reflection will be different from the translation. So on the reflection, so what we're gonna have is that the reflection will involve flipping an image over a specific axis. So we basically, or maybe we have the y-axis and then we flip the image. So that is the reflection. So it's commonly used for data augmentation, um, symmetry analysis, or image reprocessing. Remember, when we talk about data augmentation, this is one of the main ways of solving an overfitting problem in AI, where we need to do data augmentation. So when we're doing a data augmentation, we can use a geometric transformation, a reflection. So we have a reflection of images in different uh, positions. So that's what we do. So reflection or mirroring transforms an image so that it appears as a mirror image across a line or an axis, right? So we can even have it an horizontal flip, which means we have flipped it around the vertical flip, which means we flip it along the horizontal axis or the x-axis. Or we can also do a diagonal axis, but which is less common. All right, so um, that will be the reflection, which is very important. So understand the reflection means flipping an image over a certain axis by preserving the shape and the intensity, but we change the orientation of the picture. So this is widely used for data augmentation, symmetry detection, and AI pre-processing. All right, so that will be the, the reflection. All right, so these are examples of reflection. So we have an original image here where we did an horizontal reflection, which means horizontal reflection. It means we've done, we flip it around the vertical axis, which is the y-axis. And in this case, we have a vertical reflection. It means we flip it around the horizontal axis or the x-axis. So that's what we have. That. So that is a reflection. All right. So this is a diagonal reflection. All right. So all right. So the colors can also be transformed. Sometimes we can also transform the colors. So we've spoken about colors last time, where we have system with the U enhancement, we have the RGB colors. So in this case, the image U can be enhanced by processing the H component of the HSV color space. Okay, so then we can see, okay, an image from cool to warm. So this transformation can also be done there in terms of the image. We can do a saturation enhancement where we have a change as well of colors, make it a bit saturated, or we can have a brightness enhancement where we're gonna hide the brightness to the image. All right, so applications of image preprocessing in data in deep learning. Okay, guys, remember now when we were talking about all these transformation of pictures and everything, these are pre-processing the images before we can use them in the deep learning and let the AI learn from these images. So we can do a data augmentation by transforming this image, as we've seen in the few past chapters here, while we can transform images by sizes, by position, by colors, And when those images are ready, we have a proper data set, then we can use this image into an AI for the AI to learn from this image. All right. So um, in certain cases, pre-processing is not necessary. So it's not always we want to train a model that we want to do data pre-processing. So pre-processing is unnecessary for image processing algorithm in deep learning. But image pre-processing technology is used for data augmentation in training data sets. So uh, these images, sometimes we just get images and we need to use them. So it's not necessary. It's not something that you have to do every time you want to train a model. You have to pre-process the data. No, it's only when we have an issue where we will need to do data augmentation. This usually happen when you have a problem with overfitting and overfitting problem. When you have those type of issues, then you want to do a data augmentation. That's where you're going to do pre-processing, where we're going to transform this data. Okay, so to enhance image pre-processing tasks, techniques such as adding random noise to data, increasing data set sample, and improving data sample space complexity are employed. So this is how we can also solve those problems when we have overfitting. Sometimes we just have to add more uh, noise to the data or increase the data set samples instead of actually transforming the pictures that we already have. We can just add more pictures, all right? So image data augmentation commonly involves scaling, stretching, adding noise, flipping, rotation, translation, sharing, contrast adjustment, and channel transformation. All right. So this is an example of image augmentation. So when we talk about image augmentation, so in our data set, we had this type of image only. And then we realized that after training our model is not performing well. So we want to make our model more accurate. So what do? We take the same data that we have, but we're going to take all the pictures and we're going to do a data augmentation. So by doing what, instead of collecting new pictures of cats, for example, what we're going to do is we're going to transform the pictures that we already have so that the AI has more understanding of a cat. Because sometimes it means your AI is only able to identify cats that are standing like this. So you need to do an image transformation so that your AI also learn from images that are flipped or image at different position. You understand? So here we've done a horizontal reflection, vertical reflection. We've done a scaling here, translation here, and the rotation here. So this will help the AI be smarter. All right. Okay, so some essential image processing tasks that we will need. So we have digital image processing layers, which means that we have a low-level image processing where the images are processed to improve the visual effect and highlight useful information and automatic identification. Okay, and then we're going to have medium level image processing where we where specified objects in images are detected. And then we have high level image processing where the properties of objects in images and relationships between them are studied to obtain an understanding of the image content. All right. So these are the three level of image processing. Okay. So as soon as the image has been processed and identified through a neural network, we can now go in terms of image classification. If we want to classify image, so we have categories in which the images are going to be classified. So the AI is going to learn from this data and be able to classify. So image classification is one of the basic research topics of image processing in the AI field, and focus on and the focus of computer vision. So image classification determines the category of which an input will belong to. So if we place this input here or this one, and if the machine give us saying it's a row, so this was the category that was chosen. So usually in a neural network, this will be one of the outputs in the last neural network, in the last layer. The last layer will give us the outputs. Okay. Okay, so the size of K will depend on the data set. So K will determine the numbers of categories that we have. So if we only have pictures of flowers, for example, and we want to determine between these three classes, so K will be 3. So if you want to classify between pictures of dogs and cats, it means K will be 2. So we have 2 classes. So we have input and output. The input will be the image itself. The output will be the category. Which category, which will be represented by the probability value. So in this case, for example, if we say the probability from 0 to 3 to from 0 to 30%, it's this flower. From 30 to whatever amount is this flower, and from whatever amount to that is that flower. So that probability is going to be the output, which will determine the category. All right. Okay, so this is how we can do an image processing task where we have object detection. And object detection in AI is where an image can be analyzed by the machine and it can detect different objects in the same image instead of just having one image which represents one thing. But in this case, we have one image where there's many objects or there's many things on the same image, and then the machine can be able to actually choose or classify things that are on a certain image. All right, so that is how object detection can be done. And then we have image segmentation, which means image segmentation, which partitions where we partition an image in. We want to edit, for example, editing the background. The machine need to remove the background. That's what you see in certain AI apps that help you remove the background. You have even like your TikTok, and then you have a video you are talking, and then it remove your background. You have what's happening in like even in your Microsoft team or all these softwares where it detects you and differentiates you from the background and remove the background. So that is an image segmentation where the image is segmented into multiple parts, also known as regions. So we have this region. We can easily say this region represents the background, and the backgrounds can be removed from the whole image. So that is the image segmentation. Okay, so we can have image tracking. So this processing task of image tracking, that means that object tracking is just one of the area of computer vision, right? Where we use them especially with intelligent transportation, security surveillance, and human machine interaction, self-driving cars, So this is object tracking. So easily the system is not just going to get an object once, but it's going to get data of an object during a certain time. So object tracking can be used to obtain the time-based trajectory of objects and analyze the moving behavior of the object. So it's not just identifying the object, but it identifies the object and it moves along a certain scale of time. All right. So, and then we have OCR, optical character recognition. This is what is used, especially nowadays, where instead of you just uploading, when you upload on a certain platform, you upload a picture of your ID, what the platform will do is it's going to identify information on that ID and actually extract only those information. So optical character recognition, OCR, will identify the text in images and scan documents using image processing techniques such as character, object detections, and object classification. Okay, so this will improve all the efficiency as manual input is not required. So in this case, you don't have to manually input the information, but the AI is going to read by itself. So it's going to recognize the information on it. See, you can see it, for example, in malls, many malls nowadays when you enter with your car, it automatically reads the number plate and put it on your ticket. So once you look on your ticket, there's your number plate there. So this was an OCR system that was able to do that. All right, so this is another processing task in image computer vision. You have content detection. So this is when a picture can be analyzed, understood, and every object can be detected in the same image. That can be, the object can be people, like they recognize, oh, this is a child, this is an adult, what are they doing? They're playing, running, they're happy, and all those things in one image. We can have many outputs there. All right. Okay, now we also have image generation. So these happen a lot these days. Uh, People will take images and recreate certain things in the image, recreate the scene, so that is image generation. So where the AI will just generate new information on the image that were not there. So yeah. So the input can be the real image or random noise, and the output will be the generated image. So that's what we are seeing nowadays with people taking people's pictures and putting it on an AI tool, and it's gonna take that picture and puts that person in a different environment, like generate the rest of the information. Yeah. Okay, so this will be very important. So feature extraction and traditional image processing algorithm. So traditionally, what we do, we just have an image, have an image processing, feature extraction, and then image analysis and understanding. So in the image feature extraction, which means that the machine is going to look at the image sizes, each pixel, what do we have on that on that area, right? So that would be the okay. So we have your downsampling. Downsampling means that we reduce the resolution of images to be analyzed through downsampling, such as scaling. All right. So this will be when we are still pre-processing the data, so we can do a downsampling, or we can also look at the region of interest segmentation. So this is when we just want to extract a desired region from an image, right? So we don't need the whole image, but we just need a part of the image. Okay, and then we have feature decryptor, which is used as a feature decryptor to transform an image into fixed length feature vector. All right, so guys, I think this will be all for today. Uh, we'll pick it up for from tomorrow. Is there any question? All right, guys. All right.